Hello everyone, welcome to Team 32's final presentation by William, Asha, Austin, Ben, Jason, and Samuka. Our DfM project is focused on redesigning a hairdryer. A hairdryer uses electrical and mechanical processes to blow ambient or hot air over wet hair, accelerating the evaporation process to dry the hair. The hairdryer consists of an electric heating element in the form of a coil and fan powered by an electric motor that blows the air. The device provides multiple modes to control both the speed of the airflow and the temperature of the air. The hairdryer comes with a unique optional attachment, which is an airflow concentrator. Our primary customers are individual retail customers, and our secondary customers are business such as hotels, barbershops, and hair salons. The estimated potential volume of this product is 388,000 units per year. The primary customer gets the option for different attachments and/or customizable color, while secondary customers of small businesses prefer simpler and cheaper options to reduce business expenses. Here is our fast diagram. The main function is to dry hair, and we broke down the function tree as you can see to the right. Here is our functional component mapping matrix. The columns are taken from the fast diagram, and the rows are the list of parts in the hairdryer. You'll see the screws have been removed and will be optimized out. From the chart, we can also see that the rear enclosure and the rear enclosure cover perform the same functions and will be optimized later. We can also see that there are 3 separate heater ribs that all perform the same functions and will be optimized as well. Here is the product family design overview. The differentiating function is the guide airflow, which is provided by the unique attachment mentioned earlier. These are also differentiated by the color of the parts on the right. Here are the module interfaces for both the primary customers and the secondary customers. As you can see, we replaced screws at the rear enclosure with snap fit, and the secondary version also does not have the unique attachment mentioned. Here is our modified assembly sequence. You can first see that the 3 heater ribs have been reduced down to 1. We also commonized the power knob and the heater knob. Last of all, we reduced the 3-part combination of back enclosure cover, back cover, and rear enclosure into the new rear enclosure as part of our DfM improvements.
Design for manual assembly part selection module part. When looking at the functional component mapping matrix, we found that the rear enclosure, back enclosure cover, and back cover are providing the same function, and they expect them perfect for consolidation. This helps to reduce our part count, reduce needed molds, and remove 2 assembly steps. For the BOM's cost estimation, we maintain the high importance functionality of the back cover and rear enclosure while removing the low importance back enclosure cover and the high cost rear enclosure. Additionally, we will also remove 2 fasteners and replace them with press fit features in the single remaining enclosure. As mentioned in the previous slide, we combine 3 parts into 1. By doing this, we reduce part count, DfM1, we eliminate fasteners, DfM8. There are 4 other design change recommendations we found on DfM Pro, which are minimize wall thickness, keep uniform wall thickness, have draft angle, avoid sharp corners. As indicated in the table, we reduce the part cost from $4.11 to $2.60. We successfully saved $1.95 per part for part cost and 25 cents per part for assembly cost.
Design for manual assembly. The platform part we have chosen is a heater rib. Its functional importance in the quad chart is very high. The heater rib in the original design had 3 components performing the same functions, but they are placed at a different orientation at a different angle. In the assembly point of view, it's very difficult and it's a time consuming, and also the cost associated with that is also very high. Once we consolidate these 3 components into one component, taking DFA1 and 4 into consideration, the assembly time was reduced by 6 seconds.
For automated assembly improvements, the subassembly of power knob, heater knob, and speed control knob were selected. The original design of the heater knob has an oval shape, which is inefficient to roll in the shaker machine for automated assembly. The heater knob is redesigned to have a round shape so it can roll more efficiently on the automated assembly process. The redesigned shape and dimension of the heater knob is made identical to the power knob, which enabled part consolidation. As a result, the assembly no longer has 2 different knob designs, hence the volume on tooling goes up by 2 times. Also, the price per part will go down by 50%. Snap fit features were added to eliminate the need for screws for attaching these 3 knobs, resulting in part elimination and cost savings. Design for automated assembly worksheet was used to calculate assembly cost of the selected parts on both original design and after redesign. The design improvements and modified features on the three knobs, including part shape change, addition of snap fit feature, part consolidation, and part elimination, resulted in a total assembly cost savings of $2.43 based on the calculation performed using the design for automated assembly worksheet. These design changes have no impact on part functions of the selected parts. The improved design will reduce manufacturing costs due to part consolidation and part elimination. DFA design guidelines were followed during the redesign process, and they are labeled on the improved design image.
Process selection for the rear enclosure. The process is selected by considering 6 process compatibility criteria, which are 3D solid shape, 73 gram, 63 mm section thickness, 0.5 micron surface roughness, and volume of 388,000 units. As indicated in the table, both injection molding and compression molding fulfill the criteria. We selected injection molding as the injection molding is considered a more common process, which is more suitable for high volume production and is better in tolerance control. For the DfM of rear enclosure cover, as mentioned earlier, we combined 3 parts of the rear enclosure into 1 part. At the same time, we implemented the design recommendation by added radius where design had sharp corners, added draft angle to base of the part, changed part to have uniform wall thickness, and update the minimum wall thickness for mold.
Process selection for this heater rib. The heater rib is made up of aluminum alloy and a mass of 100 grams, a thickness of 1 mm, a tolerance of plus or minus 0.2 mm, surface roughness of 1 micrometer, and a batch of 388,000. Only the sheet metal working is the process which is satisfying all these parameters. Hence we choose sheet metal working as a manufacturing process for manufacturing this heater rib. Design for manufacturing for this heater rib. Once the original design is fed to the DfM Pro, it passed all the checks and was no recommendation for the redesign from the DfM Pro. We consolidated these 3 different components into single component, considering design for sheet metal 2, 6, 8 and 9 into consideration, and we come up with a single component. Coming to the cost, before design it was around $0.14. Since these 3 of the components are required for the single hair dryer, the total cost come around $0.42. After design, it was reduced to $0.3696, and the hubs doesn't give us any quotation before as well as after design.
In order to improve the customer experience and mitigate negative impacts on the environment, we plan on implementing a 2-tiered product service system. First, we will offer our primary consumers a complimentary 3-month subscription to lessons on hairstyling techniques. A 10% discount will be offered thereafter. This will serve to enhance our consumers' experience by enabling them to make the most of their hairdryer. Secondly, we will offer a 1-year warranty at the time of purchase with the option to purchase an extended warranty. This will help reduce negative impacts on the environment by extending the lifetime of our product through a repair service. Following the DFA and DFM guidelines, we reduced our manufacturing costs and time. One critique is our failure to consider how replacing Miko with sheet metal affects our heater rib, given the material's distinct properties. One other is that there are components that would benefit from analysis that we have not yet explored. If we were to start over, we would focus on creating the fast diagram and assembly sequences collectively to quickly align and streamline our optimization process. Our next steps will be to proceed with DFA and DFM analysis on all of our components to optimize manufacturing and test the performance of our sheet metal heater ribs, ensuring that they are a viable alternative to the original Miko ribs.